individual neutrons and protons combine together to form the nucleus of an atom, a tiny percentage of their mass completely disappears from the universe. This is possible because mass is a form of energy, related by the equation E equals mc squared. The energy of the mass that disappears from the universe is converted into the energy of photons. A very large amount of energy is released when even a very small amount of mass disappears. The amount of mass that disappears per proton and neutron is different for the formation of different types of nuclei. Suppose we arrange different nuclei in a row based on their total weight, with the lightest nucleus on the left and the heaviest nucleus on the right. The weight of each nucleus is determined by the sum of the protons and neutrons. The number of protons in the nucleus of each atom determines what kind of element it is. Suppose we show how much mass needed to disappear per proton and neutron in order for each nucleus to form out of individual neutrons and protons. As we move along the graph from left to right, the general trend is initially for the amount of mass that disappears per proton and neutron to increase as we move to the heavier nuclei. But after a certain point on the graph, this trend reverses. For elements heavier than iron, as we move further to the right on the graph, the amount of mass that disappears per proton and neutron decreases as we move to the heavier elements. When the nuclei of certain elements on the left part of the graph fuse together, more mass disappears from the universe, and the energy of this mass is released in the form of photons. When the nuclei of certain elements on the left part of the graph fuse together, more mass disappears from the universe, and the energy of this mass is released in the form of photons. But for the elements on the right side of the graph, the opposite is true. If the nuclei of these elements fuse together, the total amount of mass increases. This means that the fusion of the nuclei of these heavier elements ends up consuming energy rather than generating energy. In general, nuclei typically do not fuse together because the positively charged protons cause the two nuclei to electrically repel one another. Nuclei can fuse together if the repulsive forces of the positively charged protons are overcome, as they are inside the intense pressure and temperature of a star. The stars generate light and release energy by fusing the lighter elements together. The stars generate light and release energy by fusing the lighter elements together. However, since the fusion of the heavier elements only consumes energy, the fusion of these heavier elements occurs only at the moment of a star's death in the form of a supernova explosion. During a star's normal lifespan, only elements lighter than iron can fuse together. The lightest of all the elements is hydrogen, and its fusion also occurs in thermonuclear weapons, which we refer to as hydrogen bombs, which are far more powerful than the bombs that were dropped on Hiroshima and Nagasaki. Hydrogen bombs involve two nuclear explosions. The primary explosion compresses the hydrogen together, causing it to fuse into helium. The hydrogen fusing into helium releases a very large amount of energy, thereby creating a much larger secondary explosion. Nuclei fusing together, which we refer to as nuclear fusion, only plays a role in the secondary explosion. The primary explosion is created through the opposite phenomena, that of a nucleus splitting apart, which we refer to as nuclear fission. The original atomic bombs that were dropped on Hiroshima and Nagasaki were based entirely on nuclear fission. As discussed earlier, when the heavier elements fuse together, the total amount of mass increases, and this therefore consumes energy. But this also means that if the heavier elements split apart, the total amount of mass decreases, thereby releasing energy. Nuclei typically don't split apart on their own because the neutrons and protons inside a nucleus are held together by the strong nuclear force. However, nuclei can sometimes absorb incoming neutrons. Certain types of uranium and plutonium contain just the right combination of protons and neutrons, where absorbing one additional neutron makes the nucleus unstable, thereby causing it to split apart. This can generate additional neutrons, which are then absorbed by other uranium or plutonium nuclei, thereby causing a chain reaction and releasing large amounts of energy. Nuclear weapons use an uncontrolled version of this type of chain reaction to generate an explosion. Nuclear power plants use a controlled version of this chain reaction to generate electricity. Nuclear power plants help control this chain reaction by inserting control rods, which contain nuclei that absorb neutrons without becoming unstable and splitting apart. Even if a nucleus does not become unstable when it absorbs a neutron, the nucleus is nevertheless placed in what we call an excited energy state. A nucleus being in an excited energy state is similar to the electrons of an atom being in an excited energy state. The nucleus of an atom can be excited into specific higher energy levels, and the values of these energy levels are unique for each type of atom. Just as the electrons emit photons when they drop to lower energy levels, the nucleus also emits a photon when it goes down into a lower energy level. In both cases, the difference between the original energy level and the new energy level is exactly equal to the energy of the photon that is generated. Though, in the case of the nucleus, the energy levels are much further apart, and the photons generated by the nucleus therefore have far more energy. If a photon is generated by the nucleus of an atom, then we refer to this photon as a gamma ray. A nucleus does not need to absorb a neutron in order to be placed in an excited energy state. A nucleus is often placed in an excited energy state when a neutron just bounces off the nucleus. A neutron can bounce many times and travel a long distance through a solid material before it is finally absorbed by one of the nuclei. The probability of a neutron being absorbed during the collision with a nucleus of an atom depends on the type of atom and on the neutron's speed. Some atoms are much better at absorbing neutrons than others. Also, the general rule is that slower neutrons are more likely to be absorbed. A neutron will slow down the most rapidly when it bounces off the nucleus of a hydrogen atom. A neutron bouncing off the nuclei of an element other than hydrogen is similar to a small ball bouncing off a large ball. The small ball will bounce off the large ball with almost the same speed as it had before. On the other hand, the ball is most likely to lose the most speed if it collides with another ball with the same mass. This is what happens when a neutron collides with a hydrogen nucleus, since a hydrogen nucleus consists of just a single proton, which has about the same mass as a neutron. Although a neutron loses some of its speed each time it bounces off the nucleus of an atom, this never causes the neutron to stop completely. This is due to the fact that all atoms have thermal vibrations. If the neutron were to be moving slower than these vibrations, then the collision with the nuclei of the atoms would cause the neutron to speed up. A fast neutron will slow down only until it has the same energy as the energy of the thermal vibrations of the surrounding atoms. The neutron will then continue moving through the material with the same energy as these vibrations, until it is eventually absorbed by one of the nuclei. Not all combinations of neutrons and protons form a stable nucleus. A nucleus can be unstable if it contains too many or too few neutrons for the number of protons. Some types of nuclei are much more unstable than others. The more unstable a nucleus is, the more likely it is at any given moment to decay. Each type of unstable nucleus has its own methods for decaying. One method for an unstable nucleus to decay is for a cluster of protons and neutrons to break away from the main nucleus. The most common type of cluster to break away from a main nucleus is a cluster consisting of 2 protons and 2 neutrons, which is the equivalent of a helium nucleus. Another common method for an unstable nucleus to decay is for one of the neutrons to turn into a proton by emitting an electron and a particle called an electron antineutrino. Another possibility is for a neutron to turn into a proton by emitting a positron and a particle called an electron neutrino. Another possible event is for the nucleus to capture an electron, causing one of the protons to transform into a neutron and to emit an electron neutrino. When the nucleus of an atom decays through one of these mechanisms, it is transformed into a new type of nucleus, having a different combination of protons and neutrons. This new nucleus may itself be either stable or unstable, depending on what combination of protons and neutrons it has. If it is unstable, then it will keep decaying until it is eventually transformed into a stable nucleus. Regardless of if the newly produced nucleus is stable or unstable, it may be in an excited energy state when it is created. As was discussed earlier, if a nucleus is in an excited energy state, then it will eventually fall into a lower energy state and emit a photon which we refer to as a gamma ray. When an incoming gamma ray interacts with an atom, one of four things can happen. A gamma ray can pass through the atom with no effect. A low-energy gamma ray may be absorbed by one of the atom's electrons, causing the gamma ray to disappear and to transfer all its energy to the electron. A higher energy gamma ray may just transfer some of its energy to one of the atom's electrons, thereby causing the gamma ray to change direction. When an extremely high-energy gamma ray passes near the nucleus of an atom, the gamma ray can be transformed into an electron-positron pair. In this case, the gamma ray disappears and two new particles are produced.